Alright, welcome back everybody to our radiation heat transfer learning journal. So in the last video we're talking about a little bit about heat flux, right? And this is how one would calculate heat flux. Again, the physical meaning of all these symbols here were already explained. Now we want to calculate divergence of heat flux, which is again it is the physical meaning is the volumetric heat output per unit volume. So this is volumetric heat output per unit volume. On the spectral basis, well, we are doing something like this: number bullet Q lambda, Q double prime lambda. Of course, it'll be pretty trivial if one were to say it is just nabla and nabla of this quantity here, or in other words, nabla of this. Now, of course, this is the very simple way of putting things. Then it kind of makes any other video or discussion pretty pointless. But what's more important is is there some way we can simplify this expression we see here in terms of something we already know. Of course, we can use this expression, no problem. It'll be physically it means pretty much the same thing, but if we can find simpler expressions for this over here without having to go through all these integrals, it'll be very helpful, especially if we want to solve things analytically. So if we want to solve analytically, we may want to find simpler expressions for the divergence of heat flux, which is of course this. Okay, so how can we find simpler expressions? Okay, so this is the subject of this video, and oops, it's my channel. Yeah, this will be the subject of this video, and we can take a reference at section chapter 10.9 of Michael F. Modest's book. And basically yes, we want to do divergence of heat flux. Okay, we want to do divergence of heat flux, right? But if we were to look at section 10.9 or chapter 10.9 of Michael F. Modest, we'll get these two expressions over here. Now let me explain what they're doing to get this simpler expression I was talking about. So basically, where can divergence already be seen in the radiation transport equation? So normally, the radiation transport equation looks like this. It looks like this equation here. So okay, we start by this. Okay, I think this is the wrong one. Copy and paste this here. So this is the radiation transport equation. We notice that, hey, we already have a nabla down here, which is the gradient of the intensity. Okay, so to get this sort of an expression, get the divergence expression, what is basically done is to integrate over 4 pi. So just notice the left hand side, ignore the right hand side. Notice the left hand side only. Integrate over 4 pi, this expression here. So integrate for 4 pi. That's over all solid angles. S hat bullet nabla I lambda. So d omega. Okay. This is basically what you're doing. And what is being done after that is to take the nabla outside. So nabla bullet integrate over 4 pi I lambda s hat. So basically I'm taking the integral as well as the s into the divergence operator. Okay, so d omega. Now someone if you're pretty sharp, you would notice that there's a big difference between this expression here, because you can see if this is the divergence of the heat flux, because it's a nabla bullet Q. Nabla bullet Q is what we are looking for. So this should be what the heat flux looks like. If we compare to, let's say here, we notice that cosine theta is n hat bullet s hat. So this will be divergence of heat flux if Q, the heat flux, equals to whatever this integral is. So how come, okay, if we were looking at the same thing before, how come the heat flux is equals to this this thing here? Okay, so I'm just going to copy and paste this. Here's the heat flux. This. And if you notice, cosine theta is n hat s hat. Hat bullet s hat. Alright, that was what we were discussing before. So which is which? Well, then there's something we need to differentiate here. We need to differentiate heat flux from heat flux vector. So basically, heat flux is this, right? Okay, don't worry. Most things are pretty much the same as before. The differentiation here is not too critical, but we must differentiate what is heat flux and what is the heat flux vector. So remember, what we are interested in calculating ultimately is the power per unit area, and that is the heat flux, right? It's a scalar quantity. However, if we want to do divergence, this heat flux has to be a vector. So where do we get this vector from? So I'll just differentiate as follows. This heat flux heat flux is the heat flux vector. So in Cartesian coordinates, the heat flux vector, which I will denote as like this, you will have, if it's the Cartesian coordinates, you have a qx, qy, and qz. So there are different heat flux components, whereas this is the scalar. So we just want the power per unit area. So this is the final answer we get, which is a scalar, right? So that's the scalar, and this is a vector. So how are these two related? So the heat flux vector, if we were to do a dot product with the surface normal, we will get the heat flux scalar. So this is the vector. So this one will have only one component, so it is like, you know, X amount of watts per meter square, which is what we are used to calculating in the our undergraduate heat transfer courses. This will have three components: Qx, Qy, Qz. And we can see this from equation, well, let's see. There should be a very, very early on kind of a thing. Where's okay, yeah. In the heat flux part, chapter 10.8, you can see this, to obtain a total radiative heat flux, we see that, see the heat flux vector is over here. It is equal to this bit here. Right? Yes, 10.51. Perfect. Can you see the heat flux vector? Heat flux vector is this bolded Q multiplied in with dot product with the N. Likewise, it is this over here, integral over 4 pi n hat dot s hat d omega. So what I was doing on top was this heat flux vector dot product with the surface normal, okay, and we can see the relation here. You can see the Q lambda net. This is the heat flux scalar, which I was talking about. Then this Q lambda here is the heat flux vector with dot product with the surface normal. So this is the very important relation we must have here. So this is where we get it from. Alright. So this is where the cosine theta comes from. So what we have here, instead, we were to go back to our Kindle, go back. See, Q lambda, or here Q eta dot n hat equals to this little bit here. Okay. I'm going to write here Q. So I'm going to write heat flux vector like such. Bullet n hat equals to the whole shenanigans here. Blah, blah, blah. Where is it? Yeah, this whole thing here, integrate over 4 pi. Integrate over 4 pi. I lambda. Okay, so this is a Q lambda, not just any kind of heat flux. S hat n hat bullet s hat d omega, right? That is exactly what we are having here. All right. So what is the heat flux vector? Okay, so Q dot heat flux scalar is equals to heat flux vector times or dot product with the normal surface normal, and is equals to this. So actually both are correct if you define the heat flux correctly. So this one is the scalar version, and this one is the vector version. How do we get expressions for the vector version? So remember, we are trying to find the heat flux vector so we can do a proper divergence on it. Okay, so how do we get the vector version? We have to compare these two, right? We have to compare these two, and basically what we do is to bring this little n dot out. So we bring this n bullet out, and we can do that because this direction vector is pretty independent of the solid angle. Okay, and if we apply this law, the commutative law, I think it's commutative law. So let's say, okay, A, B, C. If this x vector is ABC, this vector is DEF. So what we get is AD plus BE plus CF. No, right? If we do dot product like such, we will realize that if we do the dot product the other way around, it is also the same. So, okay, I'm going to use a different color. DEF dotted with ABC. It is exactly the same. So it's AD, BE, CF. So this law actually works. Commutative law works. If I did correctly, is it commutative law? Oh yes, this is right, for multiplication. Okay, so it's called the commutative law, which means I can reverse the order. So I'll just reverse the order of the right hand side. And basically we can find out that the heat flux vector, we find that the heat flux vector is just this. So if we want, okay, so we need to differentiate the heat flux from the heat flux vector using this equation. And comparing the vectors, we find that the heat flux vector is as such. Okay, so now we have established the difference between the heat flux scalar and vector. We can continue on looking at the divergence. So what are we supposed to do divergence on? Is it the scalar or the vector? So when we do divergence, we are supposed to do this on the vector rather than scalar. So this is the scalar, which is wrong. So I'll just use a red highlight to say it's wrong. Okay, so the correct way of expressing is this: nabla bullet q lambda, I do a vector on there, equals to nabla dot q, okay, nabla dot q of this. All right, and that is what we have. However, this is actually the what we have here is that we derived the scalar version of heat flux. which is all of this, right? And to get the vector version, we need to kind of take this cosine theta and decompose it back. All right. So I'm going to remove the highlight here, get the simple version first, n hat bullet s hat, right? And then we're going to do our comparison trick again. Hat bullet okay, and have bullet that, so we find that, I mean, it's basically pretty trivial. This is just to clear up all the confusion that was there before. Yep, and then we can just substitute this whole thing here into the the expression for intensity. So, okay, that's part one, of course. I'm gonna copy and paste this here. There you go. Okay, let's do it then. Okay, yeah, but of course, yeah, we still wind up at our same problem, okay, of needing to find a simpler way of doing this. So yeah, the magic comes in, of course, knowing that this, or rather, we can find this expression from this expression here. That's the magic. We integrate over 4 pi, this, which is di ds, as we have described before. Okay, so I'm going to copy and paste everything downwards. Okay, so back to our original problem. Okay, so now that we have differentiated the scalar and vector heat fluxes, we go back to our original problem. So we have this S hat bullet, or S hat dot the divergence of heat flux. So we wanted to find our divergence of heat flux using this expression. So yeah, okay, we wanted to find divergence of heat flux using this, right? And we find out that, okay, blah blah bullet q lambda vector equals to blah blah. Okay, it should be this whole thing here, and yeah, this is the heat flux. But if we were to rearrange it, it would look exactly like this, which is quite conveniently, when you find this, it is the original formulation of our radiation transport equation, where you find this S hat bullet, the gradient of the intensity vector. So what is being done to make this look like this in this form is to integrate over all the solid angles as is stated here. Okay, so once we have established equivalence, we see that this bit here, this bit here, how do I do this? No color. Never mind. Yeah, we integrate over 4 pi, and this becomes our expression for heat flux. Q lambda vector. So this becomes our expression for heat flux, right? So how do we get this, or how do we get this, is by integrating all the expression on the right hand side. So we need to integrate the RTE expression on the right hand side. Okay, so what's our original radiation transport equation? That is over here, many moons back. DIDS equals to all of this. Okay, remember this is for like a more or less constant radiation field. If it settles pretty quickly and you can ignore the time dependence as said before, DIDS, okay, equals to nabla bullet what S hat, right? Bullet nabla I lambda. Alright, so we need to integrate all of these on the right hand side. So integrate right hand side with respect to solid angle. Integrate over 4 pi d omega I. Let's use a subscript I because this is yet another, omega there, which is due to the inscattering term. This one is a different kind of omega. Okay, which omega is this? Now the thing is that because we need to integrate over all directions coming into, let's say, a certain volume. Okay, so again, where there are two confusions here, we will need to, there's a possible confusion here, we will need to use a diagram. So this one is integrating over 4 pi of the intensity of this, right? So I'm integrating over 4 pi of this intensity, or rather DIDS. So I will need to get all this and paste here. And what is the difference between this omega and this omega? So okay, let's say you have this volume dV, and I want to integrate DIDS. So we have the divergence of this DIDS across all the dVs. So I want to integrate this quantity over this all the solid angles across dV. Right? This is integral over 4 pi d omega I. D omega I, right? So this is integrating over 4 pi here. And what is this? Okay, what is this? Okay, remember this is like this is actually the source term. All right, that is the source term. Okay. So yeah, remember we are talking about omega j in comparison to omega I. We have just discussed omega I here. So what is this omega j? So remember for each of these di ds, right? So let's say I highlight this one out using this green color. Let's just take one of these rays, right? What contributes to this di ds? There is a, all right, there's an in-scattering term. So I'll just draw in the center of this arrow. There's an in-scattering term. Let me use blue color. In-scattering term. So whatever is being scattered inwards into this arrow, so to speak, and it goes into this direction. All right, and you integrate over 4 pi. That will be this integral omega j here, because there's in-scattering, remember? So in-scattering actually contributes to this. Then when you consider the in-scattering term in this di ds, okay, for each di ds, then you have to sum up di ds over all 4 pi in this like yellow purple colored circle. So that's why we are integrating twice with respect to d omega. The first one is to account for in-scattering. So the omega j is over here as shown for this particular arrow. And so 1 omega j is to calculate for the di ds, which represents this arrow. And we have to sum up all the di ds, all these little arrows around the volume dv, in order to calculate this divergence of heat flux. So yeah, hopefully that clears up what we are doing here and why we are integrating. Why we are integrating with respect to d omega I and then d omega j. Why is there two solid angle integrations? So hopefully that clears things up. One is for the divergence, one is to account for in-scattering term. So that's why we are doing that. Now, of course, once we do that, there's some math magic that we can do, and that can show how this equation eventually gets to this, and then this will be our expression for what do you call it? This can help get us to our expression for divergence of heat flux. So stay tuned for part 2. Stay tuned for part 2. Because it's been 33 minutes this video. Don't want to take up too long, so I'll just highlight this in my favorite shade of green. Okay, so see you next time. Bye bye.